Good morning, folks. How are you today? We are in Lab 2. In Lab 2, our focus is on strengthening mechanisms and tensile testing. So, here are our objectives. We want to study the effect of a strengthening mechanism on tensile properties of a metallic material. So, in this lab, what we are going to do is we are going to determine tensile properties of a metallic alloy before and after strengthening. So I have two sets of samples. Above, I have steel samples that you are going to work on next week in your lab. And I have aluminum samples that I'm going to use for as demo. So these two steel samples have been given different strengthening amounts. Same thing in these aluminum, one is annealed and one is strengthened. So we are going to determine tensile properties of these samples, and then we are going to compare them to published values. Then in the second part, what we are going to do is we are going to make Rockwell hardness indents along the fractured specimens and study strain hardening. So in this experiment, you will become familiar with ASTM standards E8 and ASTM standards E18. So I would like you to download both of these standards so that you can study them. Please study them and you can answer quiz questions. You're of course going to critically evaluate numerical results and make summary conclusions. You're going to submit a professional lab report by next Wednesday, that is February 17th. So again, let me give you a big picture of the course. We talked about hardness testing last time, and we found out that indentation hardness correlates with strength. Whenever we make something stronger, we increase its hardness and vice versa. This lab, we are going to focus on tensile testing, and we are going to see a relationship between strength and ductility, which is inverse. So we are going to find that strength is inversely related to ductility. So that would mean that hardness is therefore inversely related with ductility. Then in the next lab, we are going to do impact testing, and we are going to find that impact toughness also varies inversely with strength. So higher the toughness, lower the strength, and vice versa. Now, in last lab, when I was giving you an overview of the course, I spoke about role of defects, crystalline defects in strengthening mechanisms. So in plastic deformation, the key point is obstacles to dislocation motion. So if we can make dislocation motion more difficult, we can increase the strength. So we spoke about four kinds of strengthening mechanisms. One is solid solution strengthening. One is one-dimensional work hardening or cold working or strain hardening. There are many, many words for it. Then two-dimensional obstacles, we have grain size strengthening. Three-dimensional obstacles, we have second phase strengthening. So in this particular experiment, we are going to talk about this one-dimensional strain hardening, and we are going to talk about precipitation hardening. We are not going to do any experiment that involves solid solution or grain size strengthening in this lab. So what is solid solution strengthening or hardening? Here, solute atoms, atoms that are dissolved, act as barriers to dislocation motion. So for example, in our sample here, we have steel. So this is the sample you're going to be working with. And as you know, in steel, we dissolve carbon in iron. So by dissolving very tiny amounts of carbon in iron, we can make steel much, much stronger than pure iron. Then the second thing we saw even in last lab is we have these one-dimensional defects called dislocations that act as barriers to their own motion. And this is what we take advantage of or exploit in strain or work hardening, which is due to cold work or plastic deformation. So all these words are kind of synonymous: strain hardening, cold work, or plastic deformation. Some are processes, and these are the result of it. Then we have grain size strengthening, whereby changing grain size, we make grain boundaries act as barriers to dislocation motion. And finally, we have dispersion strengthening or precipitation hardening. In these, basically what we have is we have more than one phase. So the second phase act as obstacle to dislocation motion. So we are going to see here, in my case, I have one is a solution annealed aluminum alloy. It has got single phase, and then by heat treatment, we create very, very small dispersion of precipitates. And these precipitates act as obstacles to dislocation motion. And we are going to find that this precipitation hardened material has higher strength. So again, giving you the big picture, we have two specimens that you are going to work on for your spreadsheet. One is labeled blue. It's a 1018 T4 steel specimen. It is skin rolled, meaning only the skin of the sample surface has been hardened or cold work. Second sample is a yellow sample, which is 1018 T3, and it is quarter hard. It has been cold worked so that it has achieved kind of a quarter of its maximum hardness. Then in my demo experiment, I'm going to work with these aluminum alloy specimens. These are 6061 T0. T0 means it is solution annealed. You're going to learn about this later on in your course, sometime like 8th or 10th week. What is this precipitation hardening? But once we solution anneal it, we have one single phase. And then we give it another heat treatment and we precipitation harden it. So what we do is by heat treatment, we create very, very dispersion of very, very tiny precipitates which harden the material. And that is labeled green. So let's look at stress and strain in tension. So what do we mean by tension? If we imagine we have a specimen, circular specimen, let's say it doesn't need to be circular, but it has an original length which is L0 and an original area which is A0. So this blue one is our original specimen. So what we do is we stretch it, we pull it by these two forces. So we are pulling along one direction only, so we call it uniaxial. And we increase the force slowly, so we call it a static tension test. We are putting this under tensile stress. So what we do is we define engineering stress, which is basically measuring the intensity of the force. So force over original cross-sectional area. So we call this engineering stress. Then we know that this sample is going to change length. Its new length will become L, longer than L0. So this change in length, delta, over original length is defined as enduring strain. So it will be L minus L0 over L0. Okay, so let's see our tensor testing curve. What happens as we start increasing the load? So what we are going to do is we are going to plot strain on the x-axis. So that's change in length over original length. And we are going to plot load over original cross-sectional area on the y-axis. Effectively, we are plotting load here. We are dividing it by a constant cross-sectional area value, original, and we are plotting here the change in length effectively because we are dividing it by a constant original length. So this is also load versus elongation curve. So what happens is as we keep increasing the load, the sample is going to keep on elongating. So first, it kind of deforms in a linear fashion. Stress is linear to strain. Then the stress strain deformation becomes nonlinear, and all this we call elastic deformation, uniform elastic deformation. The word uniform means that the diameter remains uniform throughout the length. Then it reaches some particular point, let's call it point E, the elastic limit, when it begins to also plastically deform. So we have elastic deformation and we have uniform plastic deformation from point E to M. Uniform again means diameter remains the same throughout the length. Once it reaches this point M, the maxima, the stress at this maxima is called tensile strength. It begins to neck. That means there is some middle region where the diameter changes much more than rest of the length. So it develops this neck, and from then on, most of the deformation occurs in this necked area. So we don't require as large a load for continued elongation, and our load drops, but eventually the specimen splits in 2 points. It fails. So we have fracture. Now from M to F, we call a non-uniform plastic deformation. So from O to E, no plastic deformation. From E to M, uniform plastic deformation. From M to F, non-uniform plastic deformation. But throughout, we are having elastic deformation. So elastic is not just from O to E. So let's look at what we mean by elastic deformation. And let's say we're just going to focus on that linear portion. So as we increase the load, elongation increases, stress increases with strain. And what happens is, suppose we stop at some point and remove the load. So what will happen is the stress strain curve will follow this same line back. And when the entire load is removed, it goes back to its original shape and size. So we say specimen has elastically deformed. So there are several features we see. First of all, our stress is proportional to strain, that is called Hooke's law, and the slope of this linear curve is called modulus of elasticity or Young's modulus. So we use the letter E typically. It is reversible because unloading removes the deformation. So at the bonding level, what is happening is we are stretching the bonds, but we don't break them. So when we release the load, the bonds go back to their original length and the sample regains its original shape and size. Okay, so let's see what happens once we go beyond that point E, the elastic limit. So once we go beyond point E, what happens is we have plastic deformation. So now when we unload, when we remove the load, the stress strain curve follows this dark line. So our unloading curve has the same slope as the elastic modulus. So once the whole entire load is removed, we see that we have some permanent unrecoverable, which is called plastic strain. So the specimen does not go back to its original size. So here is the entire stress strain curve. Somewhere there is the elastic limit, which we don't know what that point E is. And we have tensile strength point, point M, and then sample breaks. So let's suppose we magnify this particular portion, So our curve would look something like this. Point E might be somewhere along the line. We don't know where it is, that elastic limit. So for many curves, what we do is, in order to find what is called yield strength, a estimate of that stress at point E, we draw an offset of 0.2%, so it'll be 0.002 on our scale. Draw a line with the same slope as elastic modulus and find out where that line intersects this curve. And that becomes our 0.2% offset yield strength. So in this case, the reading is 250 MPa or 36,000 PSI. And of course, tensile strength is the stress at the maximum. So there are two measures of strength, one called yield strength when uniform plastic deformation begins, and tensile strength when non-uniform plastic deformation begins. So let's consider, for instance, two curves. Here is a material B in blue, and here is a material in red we'll call B prime. So we have these two curves, and you can see here the sample experiences a lot of strain before it fails. So this percentage strain to failure, or percentage increase in length before failure, is called ductility. So you can see this material, the red curve material, has much higher ductility than this blue curve material. So we say this blue curve material is brittle and this red curve material is ductile. So ductile materials show a lot of plastic deformation before they fail. Brittle material, practically none. So when they fracture, suppose we started with a circular cross-section specimen, what happens is when the material is very ductile, it's going to grow this dark neck. And what we will see is in a ductile fracture, we will see this cup cone fracture. These kind of lips are at almost 45 degrees. On the other hand, if the material is very brittle, the fracture is going to be sudden and it is going to be 90 degrees to our tensile axis, and our fracture surface would look something like this. So just from looking at the surface, often we can say whether the material is ductile or brittle or somewhere in between. So for ductility, we have two measures. One, we can measure the total elongation to failure. So we'll take final length minus original length over original length. A much better way, because it is often you will see it is much harder to measure length after failure. It is much, because we have non-uniform deformation. Area reduction is a much better measure of ductility. So if we measure original area minus area at fracture divided by original area, we get percent area reduction, and this is another measure of ductility. So I'm very thankful to Professor Humphrey for this video that I'm going to show to you next.
Ready? All right, so here we've got our 4 tensile specimens for the first experiment. We need to mark those up because we need to not only test them and get results from the instrument, but we also need to measure the specimens. So the first thing I'm going to do is we need to find the center of the test section, and we need to put 2-inch gauge lines. So we'll push these aside, and I'm going to measure from the corners of the test section here rather than from the end of the whole specimen, because it is possible that the test section is not perfectly centered, and we don't need to be absolutely precise about this. We just need to be pretty close. So we've got 2 3/4 inches, so half of that is 1 3/8, which puts me right here. So now I'll measure 1 inch to either side of that. And do my best to get the ruler perpendicular to the test section. Oops. Helps if we have a nice dark line. There we go. And there is our marked up specimen, first specimen. So we need 3 measurements to start with. All right, we're going to use a simple dial caliper. All right, make sure that it is zeroed. So we need the thickness of the specimen. So I'm going to measure it a couple of times and just sort of mentally do an average. So I've got 0.061, 0.062, and 0.062. We need the width of the specimen. So 0.503, 0.503, and 0.502. And then we need the gauge length. Now, this is one of those small areas where we're deviating from the letter of the law in the ASTM standard that I mentioned. It requires that these gauge marks be 2 inches plus or minus 5 1/1000ths of an inch apart. I measured and drew them with a ruler, so clearly I'm not going to get 5 1/1000ths of an inch. We're not really worried about that for our purposes, but I do need to be careful that the line does have some thickness. And so when I measure it, I need to be sure that I measure it the same way now and after we break the specimen. So I'm going to use the points on the caliper here, and I'm going to measure to the inside edge of the line. And that gives me 1.989. All right, so I'm outside that plus or minus 0.005 of an inch, but I do have an accurate measurement. Okay, so I can calculate the cross-sectional area of the specimen later, and right now we're just going to quickly mark up the other 3 specimens. Okay, and here we have all 4 completed specimens, and we're ready to start testing.
We initialize our equipment and software, we calibrate and zero the sensors. And for each specimen, we will install the specimen in grips, attach the extensometer, initiate the test, and remove the extensometer before strain reaches 5%. And then we are going to remove the fractured specimen when test is complete. So instead of doing all of these all in a single video, we are going to break it up into parts. So let's see our first video, which is installing the specimen in the grips.
This is our Instron universal testing machine. It's actually an old Model 1125 Instron frame, which was manually operated, and we've had MTS has upgraded it. So we have our main load frame here, and then here we have our control unit, which interfaces with the PC. So the motors that drive everything are in the orange base here. The main components inside these pillars behind the accordion pleats, there are long lead screws that are turned by large stepper motors in the base. That drives the crosshead here up and down. For doing tensile testing, our load cell is attached to the top side of the crosshead. That's connected to a gripper. At the base, we have a gripper that's just fixed to the base. Our specimen goes in the center here, and we pull on the specimen. The instrument will record from the load cell. It records force versus time. From the motion of the crosshead, it records distance versus time. And then with this extensometer, we can measure the actual stretch of the specimen during the early parts of the test. That's important because we need a very accurate measure of strain during the early parts of the test in order to get a good measure of modulus of elasticity. Once we get past the yield point, then stress is important, but strain is no longer as important to have an accurate measure, and so we just use the motion of the crosshead for that. So to get started, we need to launch the software on the computer here. TestWorks 4 software is what drives our MTS unit. We have several different test methods. It's basically a recipe. This one I've specifically written for this tensile test. Handles all of the everything that we need. Everything's pre-configured, so I'll accept that. And here we have our main display. We have the menus, a toolbar. Here are the main controls for operating the device. Here are some important testing parameters. So we're recording data at 10 Hertz. It recognizes that our extensometer has a gauge length of 1 inch. I've already set the grippers to have an initial separation of 4 inches, and we're going to run the test at 0.2 inches per minute. Here's our main outputs. The 3 digital displays that you can currently see are our actual measurements. So the load, the crosshead motion, the extensometer opening, and strain is a calculation. You see we've got a blinking light here. I need to reset the communications between the software and the control unit. And now we're ready to calibrate our sensors. All right, it's important always to calibrate and verify the operation of your instruments before any test. So on the Tools menu, we will calibrate. I'm going to start with our load cell. And currently we have a 2,500 kilogram load cell installed. Remove load except for grips and fixtures. That's what we have. It's calibrating the device, and the calibration for that part of the instrument is complete. Now we need to calibrate the extensometer, and the default here is not correct. We're using an MTS 1-inch extensometer. So before I actually click calibrate on this, I need to actually go to the instrument and I need to hold the jaws together. So I'll hold the jaws together gently with one hand while I click the calibrate button. And the calibration is very quick on that. It's already complete. And so that is, we now have the software set up. The instrument is set up. Now we need to actually install our specimen.
Okay, so in this video number 2, you saw how Professor Humphrey set up the machine, initialized and calibrated the sensors. In the next video, video number 3, you are going to see him install the specimen and show you proper way to align things and so on and so forth.
Okay, now that we have our software set up and our sensors calibrated, it is time to install the specimen into the grips. So you can see the jaw here has a bit of a taper to it. So as the specimen is pulled downwards, that will self-tighten the jaw. Also, if I flip the grip around here, you can see there's a backing plate on it. We're going to use that to ensure that the specimen is vertical. So we're going to put one edge of the specimen flush against that backing plate. To do this, I'm going to take my specimen, I'm going to slip it in place, and I'm going to hold it with my thumb. You can see that I've wrapped my fingers around the back of the jaw, and now use my thumb to hold the specimen in place and my pinky finger to prevent me from tipping it backwards. But now I can feel whether or not the specimen is flush against that backing plate. I also want to make sure that I have about 1/4 inch gap at the top so that the specimen is not forced up against the plate that is moved by the screw to actually tighten the jaw. So now I can begin to tighten the jaw down. Do this very gently, making sure that I keep the specimen flush against the back plate. As soon as it's snug to the point that the specimen won't just fall out under its own weight, then I stop, because I don't want to risk twisting the specimen. Now I get a firm grip on the jaw with one hand and tighten the screw with the other hand. So that now we've installed the specimen in the upper jaw. We're always going to start with the upper jaw because that's the one that has the universal joint in it. And when we unload, we'll do it in the reverse order. Now I can slip bottom half of the specimen into the lower jaw, hold it gently against that backing plate in the lower jaw just with one finger, and this screw feels backwards because it's upside down. Again, I get it snug, I let go of the specimen, and then I can finish tightening that down. Now we're ready to install the extensometer. The extensometer measures strain by the separation of the jaws. And you can see that there is a single point of contact on the upper jaw and 2 points of contact on the lower jaw. That gives us a good stable support against the specimen. The easiest way to install this is to lay it in your left palm and then squeeze the legs, the jaw, between your thumb and index finger at the very end. This allows you to hold it against the specimen where your fingers are going to be both holding the extensometer and touching the specimen. While I have it pressed gently against the specimen, I slip the springs into place. And the springs should have just a single point of contact between the spring and the specimen, and it should be opposite the feet. Okay, and so I need to adjust this lower spring. I moved it a little too far. It was going to put some torque on the specimen. Now I need to ensure that the extensometer is roughly centered vertically between my gauge lines, centered front to back across the width of the specimen, and that it's vertical, that it's not tilted one way or the other. So I can do the first just by looking at it, and visually I'm relatively close between the gauge lines, so I don't have to worry about that. To check and adjust the other two, I simply pinch the specimen from the opposite side as the extensometer. And since it's very close to the same width, I can feel whether or not it is centered top to bottom, or front to back. And if both the top and the bottom are centered, then that implies that it is vertical as well. Finally, I squeeze the jaw all the way together to make sure that it is at 0. Now that we have it installed, we're ready to start our test. Now, once we begin the test, we need to measure strain accurately in the elastic linear region of the stress strain curve in order to get an accurate measure of a modulus of elasticity. But we don't want the extensometer to still be attached when the specimen breaks. So once we get past the yield point, accurate measurement of strain is not as important. And so we can remove the extensometer at that point. The software has a set point that at 5% strain, which I know is beyond the yield point of all of our specimens, it will notify you that the removal point has been reached. Since our test is running very slowly, we don't have to pause the test in order to do this. We just come over, gently hold the extensometer, slip the springs off, and lay it down on the base of the tensile tester. This prevents the extensometer from being damaged by the shock if the specimen fails suddenly. And we're now ready to begin our test. Well, we would be ready to begin our test as soon as I put the extensometer back on again.
Okay, so our specimen is installed. We are ready to begin collecting data, and that is what you're going to see in this video number 4. Okay, so our specimen is installed. We are ready to begin collecting data, and that is what you're going to see in this video number 4.
So we've got our specimen all set up. We've done our calibration. Everything's ready to go here. We'll right-click on the digital displays at the bottom of the screen just to tear any preload. Not that we really have any. But all 3 of the direct measurements, we will 0 them for the start of the test. To actually start the test, all we need to do is click on the big green play button to run the test. It's asking for our sample ID. That's the identification for the whole data file, not just a particular specimen. So we name that typically by the section number. And I'm going to call this section VR for video recording. All right, the specimen identification, our first specimen is the red aluminum. The thickness and width are pre-programmed with the nominal values, but we want to substitute the actual values that we have. So our red was 0.062 inches thick and 0.502 inches wide. And the test is about to begin, so we know to get our hands away from the specimen. Click OK, and the crosshead starts moving. And there's our data. We've already passed the actual yield point. We've left the linear region. We're into plastic deformation. All right, you can see all of the values changing on the displays. When we reach 5% strain, we're going to get a pop-up message below the graph telling us that the removal point has been reached. 2 reasons for that. 1, the extensometer has a finite measurement range, We want to stay comfortably within that. So 5% is well within that range. Also, I've picked 5% because it's well past the yield point of all 4 of our specimens, and it is also well below the fracture point of all of our specimens because we don't want to risk having the specimen fracture while the extensometer is still attached. This test is running very slowly, so I can just slip the extensometer off without interrupting the test. The data is seamless because the test method is programmed that as soon as we hit that 5%, it stops measuring strain directly from the extensometer and starts calculating strain based on the motion of the crosshead. That's less accurate, but strain is less important in the plastic region. An accurate measurement of strain is only critical in the linear region. So we're approaching the maximum load. The load is not going up very quickly anymore. Once the load levels off, we'll have reached the ultimate point, maximum stress, the tensile strength for this material. Once the load starts to drop, then we'll examine the specimen to look for the neck. And it looks like the load is starting to drop. So I'm going to look closely at the specimen here. And I can see the neck beginning to form right here. It's actually first visible as a discoloration. Now I can see the fracture actually in there. And anticlimactically enough, our test is complete. The software monitors the load, and when the load drops below 20% of the maximum that it had recorded during the course of the test, it decides that we've had a fracture and the test is over. On the screen, it's telling us the crosshead is about to return. We do not want to click OK at this point. If we return the crosshead now, it'll mangle our fractured specimen. So I first need to unload the specimen. So I'm going to unload from the bottom first, the reverse order that we loaded it. Carefully release the clamp. You can see that there's 2 small threads of metal to either side, still holding the specimen together. It was supporting about 40 pounds of load when the test finished. So if I'm careful, I can remove the specimen, and it is still more or less in one piece. If I look at it carefully, I can actually see through the fracture, and again, there's just 2 small bits of metal at the very edge still holding it together, but it would not take much to finish breaking that. Now we can return the crosshead, click OK, and the software automatically takes us to the review screen where we see our stress strain curve, and there's a number of points on there, and we'll look at that in more detail once we get all of the data in place. So now I'm going to load up the next specimen and run the remaining tests.
Okay, now we need to measure final length. To measure final length, we need to put the specimens together and measure them manually. So here is Professor Humphrey's last video where he shows how careful you need to be in making those manual measurements.
Okay, so we're going to measure the final length of our specimens. Now, despite the fact that many of them came out of the tensile test still marginally in one piece, I've deliberately finished breaking them in order to demonstrate the correct method for measuring the final length. So to measure the final length, you take the 2 halves of your specimen and you basically fit them back together as well as possible. And then you hold them in that position. And now I'm going to measure the same way that I measured before. So I measured from the inside edge of the line, and I'm actually going to press the point into the metal so that it stays put. Well, or that's the theory. And I come up with a measurement of 2.576 for the red. So our final length, 2.576. Now I'm going to repeat that with green, blue, and yellow. Again, I'm going to hold those together. This will be easier with multiple people, where one person can hold it together and the other one can measure. And I get 2.225 for green. And I get 2.804 for blue. And 2.662 for yellow.